can continue now with the second plenary lecture of this afternoon. And it's a pleasure for me to introduce Professor Boyce GRIFFITH. And I would like to introduce you. Professor GRIFFITH is coming from the University of North Carolina and is the leader of the Cardiovascular Modeling and Simulation Laboratory. And his research interests are mainly the mathematical modeling and computer simulation in medicine and biology. In particular, his main topic is the Immersed boundary method, and he comes from a celebrated school for this topic, and in particular for the application of heart valves. And he has also involved in the numerical solution of Navier-Stokes, image-based CFD for ventricular blood dynamics, cardiac mechanics, electrophysiology. So all the cardiac function was studied by Professor GRIFFITH. So please, today the topic is fluid structure interaction for the cardiac function. Please, thank you.
Thank you very much for that introduction and for the opportunity to present some of our work on modeling fluid structure interaction in the heart. So this talk is gonna have a lot of concordance with the previous talk. We're with a little bit more of a focus on applications of methods for fluid structure interaction. So yesterday, Professor Guccione gave a great introduction to heart failure and to valvular heart disease. Today, at least for the first part of my talk, I'm going to be more focused on the aortic valve. So these are images of on the left a healthy aortic valve, and on the right severely calcified aortic valve. And so these calcific lesions that form in the aortic valve result in an increase in flow resistance, and ultimately can result in severe aortic stenosis. Aortic stenosis is a disease which has a prevalence that increases very rapidly with age. So in the United States, prevalence is about 8.5% for people that are aged between 65 and 74, but it rises to about 13% for people over age 75. Globally, there are tens of millions of cases of calcific aortic valve disease and degenerative mitral valve disease. And the only effective treatment for these severe valvular diseases is either repair, which is primarily performed on the mitral side, or replacement, which is done for both the mitral and the aortic valves. And these are examples of valve replacement devices. I'll get into more details on this a little bit later in the talk. So what I wanted to do today is to give an overview of the kinds of methods that we develop and use for modeling valve function, valve fluid structure interaction, and then to show examples of applications of these methods to simulate fluid structure interaction, both in vitro and in vivo settings. The goal ultimately is to have tools that can help to aid in design and regulation of treatments for valvular diseases. So the kinds of methods that we use are immersed methods, or immersed boundary methods. So the sort of classical immersed method is the immersed boundary method. This was introduced by Peskin in the 1970s. And the basic idea with the immersed boundary method is that we're going to use an Eulerian description of the fluids. We're going to describe the fluid in fixed physical coordinates, say lower x, x1, x2, x3, and we're going to use a Lagrangian description of the immersed structure. And so for the classical immersed boundary method, the structure was a boundary, but we're going to keep track of the deformations and the resultant forces generated by the deformations of the structure in terms of a material coordinate system that's attached to the moving structure, and then we're gonna link these two descriptions together. So in the continuous equations of motion, what you wind up with are the Eulerian incompressible Navier-Stokes equations, except that they're augmented by an additional force. And the case of a boundary, we're going to have a boundary force. I'm going to be a little bit vague about where this force comes from for now. I'll be more specific in a few slides. But we have a boundary force, And this boundary force is defined with respect to the Lagrangian coordinate system, and we're going to convert it into an equivalent Eulerian body force density by taking that force and integrating it against the Dirac delta function kernel. And then we're going to use a similar integral transform to go from the computed Eulerian velocity field to the velocity of the boundary. So when we discretize these equations, sort of a typical thing to do is to use a fixed Cartesian grid for the fluid, and we're going to use a body conforming mesh only for the structure. And we're not going to attempt to make the discretization of the structure and the fluid conformal. And instead, what we're going to do is we're going to replace the singular delta function with a regularized version of the delta function, and that's going to allow us to avoid constructing body conforming grids. So there are a lot of different ways that you could construct a regularized delta function. This is a construction that I particularly like because it's very simple. And so this is a construction for the cardinal B-spline. So you start out with a sort of a zeroth order B-spline, what's called the window function. And if you convolve the window function with itself, you get the hat function, which is the sort of first order B-spline. And then you can continue recursively. You can convolve the first order B-spline with the window function to get a second order B-spline, so on and so forth. And these functions are nice because they're piecewise polynomial, and they seem to have nice properties when you use them with the immersed boundary method. So just to kind of briefly walk through the way that the simplest version of this method would work, we're going to start off by computing forces on the structure. We're going to take those forces, we're going to smear them out onto the background grid using this regularized delta function. You solve the incompressible Navier-Stokes equations to get a velocity that you then sample to get the velocity of the structure, and then that allows you to sort of induct the structure in a way that satisfies that satisfies all the matching conditions that you want to satisfy along the fluid structure interface. So there's been work for about 15, 20 years now to extend immersed boundary methods to what you might call an immersed body method, where you have an elastic structure, volumetric elastic structure that's immersed in a viscous incompressible fluid. These kinds of methods are set up so that you can take advantage of say, hyperelastic constitutive models to describe the response of the immersed structure. The simplest way that you can do this, you wind up with sort of a superposition in the solid region of a fluid-like stress and a solid stress. And so that solid stress is going to come from, say, a hyperelastic material model. And in this way of doing business, the idea is that you're solving a single momentum equation everywhere in the computational domain. So we're going to solve the momentum equation everywhere in the computational domain. Inside the structure, there are additional forces that come from the divergence of that structural stress. Along the interface, there's an additional sort of traction-like force, a transmission force that's required to satisfy the right matching conditions along the fluid structure interface. And so really the only difference between the classical immersed boundary method and these kinds of immersed body methods is that the way in which you compute these forces and transmit them to the background grid. One thing to note about this is because we're using a common momentum equation for the coupled fluid structure system, at least in principle in the continuous equations, the structure is automatically incompressible because the velocity field satisfies the divergence-free condition everywhere in the domain. And then in practice, we want to use this kind of a formulation using a finite element structural discretization. And so to do that, one thing that you can do is just get an equivalent body force by integrating by parts. And if you do this sort of the right way, then this transmission force term winds up vanishing, and you're back to a method that in terms of the way that it works is very, very similar to this classical immersed boundary idea that I introduced a few slides ago. And then of course, finally, we're going to replace the singular delta functions with regularized versions of the delta functions. So just really briefly, so does this work? So and the answer is it depends. If you don't set things up correctly, you don't get very good results. But if you're careful, and we talk about in this paper that I think actually that should be 2020. But so this paper, how to do things properly, and you can get good results. So this is a standard solid mechanics benchmark. We're doing an FSI computation, but so it's a twisted beam. If you look at say the principal stretches under grid refinement, we wind up retrieving results that are in good agreement with sort of benchmark, just regular structural finite element mechanics results. This is a more interesting benchmark. So this is part one of the Hessenthaler benchmark using a slightly different method that I don't have time to talk about right now, although if anyone's interested, I'd be happy to chat about it in the coffee in a few minutes. But so this is looking at the so-called phase one of the Hessenthaler benchmarks. This is steady flow conditions. And we're looking at the beam deflections and comparing them to experimental data, and we get good agreement for the steady case. And then the phase two of this benchmark is looking at unsteady conditions. And again, we get, I would say, pretty good agreement with the time-dependent deflections of this beam. So this is a case where there's an experimental data set that you can use to sort of validate that this FSI methodology, or that one's FSI methodology is working. Okay, so that's all I wanted to say about methods. So I'm going to switch gears and start talking about some applications of these methods, and sort of in the same vein of the previous slides. One of the things that we're trying to do is to sort of validate that the models work. And so the system that we're using to perform initial in vitro validation is a pulse duplicator. So it's a tabletop sort of heart simulator. The particular system that we're using is sort of a model of just the left side of the heart. It's got a flexible left ventricular bag. It's got a rigid left or sort of atrial chamber. There's a mitral valve here. It's just a simple spring pump, a simple spring valve. And then it's got a outflow tract and a model of the ascending aorta. The bag is modulated by a programmable piston pump. And so the way that this works, there's water outside of the bag, and then there's a test fluid inside of the bag that is in this contiguous flow circuit. Test fluid is typically saline or glycerol solution. And a nice thing about this particular setup is that you can interrogate the flow of fields using techniques like particle image dosimetry. So just really briefly, we've looked at both pericardial bioprosthetic valves and porcine tissue valves and these kinds of systems. We have models of these devices that include features of the real devices. So the pericardial bioprosthetic valves have an engineered fiber structure, and the tissue valves have a fiber structure that's like a native valve. The kinds of models that we use to describe the mechanics are things like this Hopsepple-Gasser-Ogden type model, where you have something like a isotropic matrix along with fiber reinforcement, and you can use these kinds of models to get good fits to available tensile test data. And so we've taken these models of the valves and put them in a model of just the aortic test section of this pulse duplicator system. And we're using reduced order models to talk about the upstream components of the pulse duplicator. So this flexible bag, the piston pump, as well as the downstream components. So downstream of the aortic test section is a classical a wind kessel, so compliance chamber and a resistance. And so we separately tune up boundary models using available experimental data. So we tune up the upstream reduced order model, and we tune up the downstream reduced order model, but we do that totally separately from the FSI model. And then we plug it all together and we ask if we get reasonable agreement in terms of pressures, flows, and valve dynamics. So this is a plot looking at the flow rate, and the experimental data here is in this dashed line, and you can see this is actually averaged over in this case 10 consecutive cycles. And so here in this particular model, we're only prescribing the flow rate at the pump. So pretty far away from the FSI model, but we're getting, I would say, good quantitative agreement with the flow rate. And so this is I would argue this is a pretty non-trivial test, because we haven't done anything to tune up any of the boundary models to give us a particular flow. And if we get the wrong pressure volume relation in this moving domain, then well, this isn't going to work. And we get, I would say, better agreement for the pressure. So this is the driving pressure. This is the loading pressure. And a crucial thing, if you want to model multiple cycles, is that the closed valve closes. It doesn't leak, and it supports a realistic pressure load. This is a way of quantifying the valve dynamics. It's very valve kinematics. It's a very simple way to do it. We're looking at the open area of the valve as a function of time. And here we're getting, I would say, not so good agreement with the particular experimental case. So here we're getting fluttering in all three of our leaflets. This particular video only shows fluttering in one leaflet. This particular valve was a little bit twitchy. Sometimes you would get fluttering in all the leaflets. Sometimes you'd only get one. But the frequencies are, I would say, pretty similar. And again, we don't actually know the biomechanical properties of this exact valve. And so this is using a sort of generic model of the biomechanics of the flexible leaflets. Okay, so we've looked at whether we're resolving flow structures, and I would say that we're doing a reasonable job of capturing the large-scale flow structures. So this is looking at the axial flow under increasing grid resolution. So you can clearly see that we're getting more complicated flow structures with higher resolutions, as you would expect. But the large-scale structures are largely in agreement. So there's this big recirculation zone that's downstream of the stent. We're getting recirculation in the model of the aortic sinus that shows up in this in vitro sort of model. Okay, so we're working towards validating this using flow fields using particle image dosimetry. The challenge is refraction index matching. So we wind up needing to use calibration in order to get quantitative flow information out of these kinds of experiments. And these are comparisons of experimental and simulated flow fields downstream. The blocked out region here is the sinus. So we don't really trust our velocity measurements in the sinus region. Looking at flow profiles downstream of the valve at sections ABCD is increasing distance from the valve, and we have, I would say, reasonable agreement with the flow field. So the flows are very complicated. These are nearly turbulent. We're capturing the right flow rates. We're capturing roughly the right flow profiles. There's still more work to be done here for sure. This is definitely work in progress. Okay, so what can you do with this? So one thing that we've used these models to look at is are the geometrical determinants of prosthetic heart valve dynamics, the leaflet dynamics. So I showed the valve was fluttering. So is the fluttering real? So we looked at the dynamics of initially 3 different size valves where we had matching experimental data. So 27, 25, and 21 millimeter valves. And one thing that's sort of striking in this simulation, or in this comparison of simulations, is that the smaller valve, I think it's very clear, it flutters at a higher frequency than the larger valve. So this is another view looking straight down. So this is the smallest valve. So smallest valve flutters quite violently compared to the larger valve. So is this real? Well, so I think it's real. So this is a comparison between computational experimental leaflet fluttering dynamics, again, as a function of valve diameter. So here we're quantifying the valve dynamics experimentally, again, using this open area sort of waveform. And the smaller valve shows very violent fluttering, both in the simulation and in the experiment. The largest valve, so this 27 millimeter valve, shows markedly less fluttering. And so again, the dash curves here, it's maybe a little bit hard to see, are the experimental data with again 10 consecutive cycles. And so both the experiments and the simulations show that there's a marked decrease in fluttering frequency as you make the valve diameter larger. The relationship is not in perfect agreement between the two, but the general trend is captured. Okay, so you can also ask, well, what happens as you change the leaflet thickness? And so as you change the leaflet thickness, what you end up seeing, for say this is the thinnest case, this is a thicker case, and then the middle is showing a case that corresponds to the sort of standard thickness. You see that there's similarly a increase in fluttering frequency as you go from a thinner valve to a thicker valve. Unfortunately, we don't have a good way, at least at this point, of validating this prediction experimentally. It's hard to control the thickness of the valve leaflets, and also while preserving the mechanical properties. So we're looking into this. So those were simulations and experiments that were all done using standard test conditions, which actually use saline. So the viscosity is about a quarter of the viscosity of blood. These are, and so you might ask, in those cases, is the fluttering, again, is it real? Does it show up in physiological conditions? Here we're looking at what happens over a broader range of valve sizes at physiological Reynolds numbers, and you see the same trend. Smaller valves, smaller diameter valves flutter at a higher frequency than the larger diameter valves. Okay. All right, so what are the summary sort of points? So I think it's pretty clear from both experiments and simulations that these smaller diameter valves have markedly higher fluttering frequencies. And this seems to hold across operating conditions. So we see this in saline, we see this in a glycerol solution. And I think that we have, in terms of these dynamics, very good agreement between the experimental and computer model results. We have this other prediction that we haven't validated yet, which is that thicker valve leaflets generate higher fluttering frequencies and smaller fluttering amplitudes. I think this is kind of an intuitive thing. So if you think about keeping the mechanical properties fixed and making the leaflet thickness larger, it's sort of like a stiffer and stiffer beam. And so you would sort of expect that the fluttering frequency would go up and the amplitude would go down, but this is actually at odds with some other computational work. And so it's, I think, not totally clear that this is right. Both of these results have implications for both surgical and transcatheter valves. So it's been known for a long time that patients that receive surgical valves, that receive smaller surgical valves, are at a higher likelihood of developing what's called patient prosthesis mismatch. So basically early valve failure. And this hasn't really been explained in the surgical literature. We think that it could be that these higher fluttering frequencies are resulting in more wear and tear on the bioprosthetic valve leaflets and are resulting in earlier valve failure in these smaller valves than in the standard or than in the larger valve diameters. The results are also important for newer transcatheter valve leaflets, because transcatheter valves, ultimately what you want to do, as I'm going to show in a moment, is to crimp a stent-mounted bioprosthetic valve as tightly as you can. And so in order to do that, there's an advantage to using thinner biomaterials. And so you might worry that a thinner valve leaflet might wear out faster. So insofar as fluttering is important, if it's true that thinner leaflets do not have as high fluttering frequencies, you might actually see better durability of in these TAVR devices at smaller diameters than with surgical valves. Okay, so transcatheter valve replacement. So the idea with transcatheter valve replacement is it's not so much replacement as well, you're deploying a stent-mounted valve on top of the disease valve. So the first human transcatheter aortic valve replacements were performed almost 20 years ago. They were initially only available for patients that were at high risk of surgery, but they're now approved for essentially all patients that require heart valve replacement. And the initial devices are for the aortic valve. There's very active development of devices and procedures for the other valves, including the mitral valves. So these are examples of devices for the mitral valve that are in development. So some complications with TAVR include paravalvular leak. When you deploy the valve, you can potentially push on the AV node. This can result in AV node block. There's a phenomenon called reduced leaflet mobility that may be related to leaflet thrombosis. It's not so clear how durable these devices are. They haven't been implanted for all that long. A lot of the complications and challenges involve fluid structure interaction. Computational models, I think, are very important here. Insofar as fluid structure interaction is important for the performance of these kinds of devices, because it's very difficult to clinically image the flow fields around these valves. Okay, so we have put together a patient-specific aortic stenosis model. So here we don't have specific discrete calcium nodules. We've sort of made the leaflets uniformly stiffer. But we've been able to set up a model that corresponds to a patient that received a TAVR device, and And one thing that sort of was surprising to me is how small the open area can be, and still actually get this corresponds actually to sort of mild aortic stenosis. So this is a mean pressure grading of about 15 millimeters of mercury. So we put together models of the core valve. Core valve is a self-expanding device. The stent's made of nitinol, which is a shape memory alloy. Can model the crimping process. We need to be able to crimp the valve in order to deploy it. So then we're gonna deploy the valve. We're gonna load it up with a transvalvular pressure load. So this is about a sort of a diastolic, sort of like an end diastolic pressure difference across the valve. And then we're going to drive forward flow through it. So so all of the contact here is being handled sort of automatically by the immersed boundary formulation of FSI. And so in particular, we're sort of directly simulating contact between this transcatheter device and the model of the native aortic valve. And with these kinds of methods, I mean, so they have pluses and minuses, but one plus for them is that you don't need to have predefined contact surfaces in order to model these kinds of contact problems. We have similar models of the Sapien valve. So the Sapien valve is a valve that has a steel frame. It's balloon expandable, and performs similar kinds of computations here. Deployed the Sapien valve, loaded it up. And then we've run forward flow through this. And you can see actually with this model, for better or for worse, we actually are getting paravalvular leak. And so whether we should be getting paravalvular leak in this particular case, I don't know, but it's something that the model is able to capture, which I think is a strength of these kinds of, this kind of a modeling approach. Okay, so do these TAVR devices do sort of what they're supposed to do? So mean pressure difference across systole for the basic stenotic model is about 15 millimeters of mercury. And then deploying these models of the transcatheter valve devices, we wind up with pressure differences of about 6.5 to 7 millimeters of mercury, which is what's seen clinically when these kinds of valves are used in patients. Okay. So one of the emerging concerns with transcatheter valve devices is this finding of what's called subclinical leaflet thrombosis, and this was found in clinical trials of new TAVR devices. And actually, there's elevated rates of subclinical leaflet thrombosis, so thrombus that forms on the bioprosthetic valve leaflets that's not severe enough to require urgent surgical interventions. This happens following both transcatheter and surgical aortic valve replacements at rates that I think are higher than what were expected. And there's recent data that shows that there's actually, and concerningly, a statistically significant increase in clinical valve thrombosis following transcatheter valve replacement as compared to surgical aortic valve replacement. There's not yet a mechanistic explanation for what's going on. It could be related to crimp-induced leaflet damage. It could be related to abnormal diastolic flow patterns. And we're working to put together models to investigate this. So this is kind of a proof of concept simulation where we're simulating fluid structure interaction as well as the dynamics of a chemical species that's being transported by the flow and that can interact with the valve leaflet. So here, this is not a model of thrombosis, but it is a model. Well, it's a simulation showing that we have a methodology that allows for interactions between a bulk concentration and a surface bound concentrations in the context of fluid structure interaction. And so what's happening here is that as the concentration increases, this leaflet is getting stiffer and stiffer. So it doesn't get quite stiff enough for you to really see that it doesn't open. But at any rate, so these kinds of methods we hope we can use to say something useful about leaflet thrombosis. All right, so I'm almost out of time. I do want to quickly show some results of a fluid structure interaction model of the human heart. So we've been working for several years now on a whole heart model. This model includes descriptions of all the major features of the heart, the 4 chambers, the 4 cardiac valves. It has representations of at least the initial parts of the great vessels. At this point, we're using a model that uses a fully conformal structural mesh for all of the structural components. And to generate this, we've been using this open source software that I think is sort of amazing called TEPWild that can generate these really complicated meshes that include both thick volumetric structures and really thin structures like the chordae tendineae. We have CT data that will allow us to define the anatomy, the anatomical geometry of the chambers, but we have to use model-based approaches for the valve leaflets. We can't clearly see the valve leaflets. And similarly, we need to use model-based approaches to describe the fiber structure of the valve leaflets. And so this is using Poisson interpolation kinds of methods that are now fairly commonly used to also construct fiber structures for the heart. And so you can use these kinds of constructions to get fiber structure for the ventricles. We're doing a whole heart model. We need to have it for the atria as well. We're using biomechanical models for all of the structures of the heart that come either from tensile tests from human tissue specimens or that have been inferred from medical images. So in the simulations I'm going to show you, the ventricular mechanical properties are inferred from imaging data. The rest are from tensile test experiments. We actually are in the process of switching over to a version of this where it's all using tensile test data. We're using an active strain formulation, which we found in this particular model to allow us to handle things more stably. We can take larger time step sizes. The whole thing is hooked up into some really simple circulation models, so we don't have a closed circulation at this point. It is important to account for pericardial tethering to get reasonable deformations of the heart wall. And so these are examples of what this model does. So this is a full cycle. It automatically has isovolumetric contraction and isovolumetric relaxation. We're getting realistic cardiac output and ejection fractions. We are getting this big pressure spike in the left ventricle. I think I know how to fix it. We'll see. This is just slowing things down just a little bit. And again, so all of the dynamics here are the result of fluid structure interaction. Then this is just a visualization looking at the flow fields here. I think I am over time, so I'm going to well, I'm gonna skip my summary slide and just put up acknowledgements, and thank you very much for your attention.
Okay, thanks. You have some minutes if you want to conclude
okay, all right, okay.
Because
right.
we have 8 minutes, so
okay.
if you want for the discussion for us is good.
Okay, all right. I'll just say some things very quickly. Okay, very quickly. Very quickly. All right. So these, what I would describe as modern immersed boundary methods, they're able to treat fluid structure interaction models that have very complex geometries and can incorporate detailed constitutive models. If you're careful, you can get them to provide accuracy for structural mechanics kinds of results that are comparable to what you would get with the conventional finite element method specialized for solid mechanics. We're able to get good agreement with simplified experimental FSI benchmarks. We've been making progress, I think. I hope we've been making progress towards actually validating that these kinds of models of heart valves are able to give reliable results. And at this point, we have much more validation for the surgical valves, which are they're of less interest, but you can also use these methods to look at transcatheter bioprosthetic heart valves as well. In all of these simulations, the leaflet motions are not prescribed. How the valves open and close is not prescribed. The flow rates and pressure differences are not imposed directly. All of the dynamics in these simulations are generated by interactions between detailed FSI models and reduced order boundary models. But at the end of the day, the way that the valves open and close, the way that the leaflets contact each other, the way that the structure, the stents interact with the aortic root is not prescribed in advance. I think we have some interesting agreement with the predicted fluttering dynamics, and this could explain the apparent reduced durability of these smaller diameter valves. And then we've extended these kinds of models also to simulate FSI in the heart. We're able to generate, I think, realistic cardiac output. There are a few things that are almost done that I think are gonna improve the results quite a bit. They're not done yet. I can't show them to you, unfortunately. There's some work that we still need to do to get this model where we want it to be. We want to close up the circulation. We need to tune up some of the features of the right heart. but I think we're very close to having sort of a normal heart model, and then we need to make it sick. Okay, so that's everything I wanted to say in terms of conclusions. So the work I showed you was done by for the valves. Most of the work was done by Mike Lee, who's now at Johns Hopkins, and Robert Hunt, who's a math PhD student finishing up now. Jordan Brown did all of the TAVR simulations, and Marshall Davey and Charles Poles, along with Simone Rossi, are really leading the charge in putting this whole heart model together. And now I'll stop. Thanks.
Okay, thank you. Thank you very much for this very inspiring lecture. And I would like to open the discussion with Professor Griffith, please, if there are any questions. Okay, I would like to start with a question from the chat. So Miguel Fernandez, sorry Miguel, I did not understand that you would like to have a question. If you want to write your question by chat, I can read for you to Professor Griffith. In the meantime, if there are other questions. Okay, if not, okay, Paolo, please.
Hello, Boyce. Thank you very much for the beautiful lecture. My question is about a little bit on the methodological side, if you want to make a comment. I mean, obviously you started saying that the Immersed Method is based on an approximation on the Dirac delta. How much the different types of approximation can be used may influence the properties of the method, and how much care would you suggest in this particular aspect of the method?
Yeah, so that's a great question that I think hasn't been very systematically investigated in the literature. So the properties of these delta functions matter, it also depends on the flow regime that you're looking at. So the flow regimes that we're looking at, what we seem to want to have are we want to have kernel functions that satisfy that allow us to ensure that force and torque are conserved. So that seems to be pretty important, and that are fairly smooth, but that are not too big. So so this B-spline construction gives you bigger and bigger and bigger kernel functions, and it converges to the Gaussian, which seems like a nice function to use. Maybe not. I don't know. But it seems important to use sort of a compact kernel function, and we have a preprint that demonstrates that using these more compact kernel functions gives you much more robust results across grid spacings, and so that seems to be important. So there's another thing that you can do, which is you can set up these methods and sort of not approximate the delta function if you think in terms of the delta function formulation is equivalent to a jump condition formulation. And if you, instead of, you get a method that has almost, well, I mean, it works basically like the inverse boundary method, but instead of smearing out forces, you have forces that correspond to what has to happen to give you the jump conditions. And these kinds of methods are much more accurate, and they're a little bit twitchy. But so these kind of methods are like immersed interface kinds of methods, and we're moving into trying to use those. As we make those kinds of methods more robust, we're going to start replacing kind of regularized delta function approaches with stuff where we have sort of sharp jump condition based formulations. But at the end of the day, kind of the way that the computation works is very analogous. You don't need to have conforming discretizations between the fluid and the structure.
Thank you very much.
Okay, I can read the question by Miguel Fernandez from INRIA. Very nice presentation, he said. And the question is, I do not understand how contact is handled. We don't see the leaflet getting into contact. Yeah.
So this is a great question. Let's see. Let me see if I can. Find an example. So right. So there's a gap. And this was highlighted at least obliquely in the previous talk as well. I like this slide because well, anyway, so all right, so there's a gap. So what is that gap? That gap is the physical size of the regularized delta function. So they're force. You can think of there being forces that are concentrated in the structural model just along the volumetric mesh that we're using for the leaflets, but those forces get smeared out over an additional volume that corresponds to this regularized delta function. And so here what you're seeing effectively is sort of the background grid resolution. The leaflets weighing up about a mesh width apart or so. But you have a contiguous force that shows up, and the result is that for instance, if you look at this kind of a plot here, this is the transvalvular pressure difference when the valve is closed, right? So the leaflets, they can't interpenetrate each other. They're generating a force that prevents there from being flow. And so you get the pressure difference across the valve that you want. So in some sense, the immersed boundary method with regularized delta functions gives you an implicit contact model. So so if you want an implicit contact model, that's good. If you don't want an implicit contact model, that's bad. I'm not sure if that adequately addressed the question. I'm happy to talk about this more in the discussion later.
Okay, thank you, Alfio.
Boyce, thank you very much for this very interesting talk. Can you please comment on or give some more details about the say the size of the space discretization and the time step, and so how long does it take to simulate, say, heartbeat? Just the competition.
Yeah. So let's see. So like. Let's see. Okay, so like for these aortic valve simulations. So here we're using a computational domain that's equivalent to like a 320 cubed grid. The length is about 10 centimeters. You wind up with about a quarter millimeter background grid cell, something like that. That's in the order of the background grid spacing. And so that's kind of comparable to the structural discretization as well. These computations are running on we do things using resources that are available here. So we have some nice beefy servers, but they're not like, we don't run these on gigantic parallel systems. So running one of these models on like a modern AMD, we have these Epic chips that we like, but just a single server takes about a week per cycle. So it's slower than we'd like, but it's also not a gigantic computation, and it's something where we can run lots of cases all at the same time. But so these are still slow, and it's something that we're definitely working on. The heart simulations are slower yet. So those take a couple weeks per cycle. Again, running on these individual servers, not running on gigantic parallel systems. We do have a software infrastructure development effort that's working to improve parallel performance. So we can sort of, so we'd like to be able to in principle scale things up to really gigantic core counts. Although again, I don't know how practical that is if you really want to do lots and lots of cases. So if you need to do lots of cases at the end of the day, and you need to use lots and lots of cores to get your cases done, then you're going to have some limitations. So, but yeah, so these are slow. These are definitely slow. We're working to make them faster. There's there's some numerical challenges that have been vexing to do things like improving the time step sizes. So these are so I didn't answer your other question in terms of the time step sizes. You're talking about sort of kind of on the order of hundreds of thousands of time steps per cycle. So these are very small time step sizes.
Thank you. Is it? I mean, do you have a constraint on the stability, temporal stability?
Yeah, absolutely. So so the coupling that we use is kind of like what I sketched out kind of at the beginning of the talk. We use something more complicated than this, but basically we compute forces, we put the forces on the right-hand side of the Navier-Stokes equations, we solve Navier-Stokes, then we use the velocity to move the structure. So it's explicit coupling between the fluid and the structure. And so with the way that we're doing things, it's sort of like it's like using an explicit method for the structural mechanics, even if you're using sort of a semi-implicit formulation for the Navier-Stokes equations. So if you've got a stiff material or if you've got penalty forces, that can really result in tiny time step sizes. So we've been working for a long time to come up with efficient implicit formulations, and the numerical linear algebra for solving the coupled system implicitly is challenging. And so we have methods that allow us to take big time step sizes, but the solvers are expensive enough that that it's cheaper to just do things explicitly. So we have a couple of approaches that are more like distributed Lagrange multiplier approaches that I think might allow us to start to separate the timescales for the fluid and the structure at least, and to start taking larger time step sizes. But those things aren't quite ready for production use in real models.
Thank you.
Okay, we can thank again Professor Griffith. I remember